causal decision making. So I guess you are all well aware of decision making, and I'll try to explain a bit what I mean by causal decision making. Can I remove maybe this? I'm not sure how to do that.
You should click on the chat in such a way because it came out because of the message.
Or you can also do more.
Thank you, Amar.
And also probably the window.
Can I do that?
Down. We can.
This?
Yeah, we can.
Okay, that's fine. Okay, so causality. It's kind of a hype word in machine learning, maybe in other fields as well. And there are many terms: causal inference, do calculus, confounding, deconfounding, interventions, causal graphs, counterfactuals. Maybe you've heard about some of them. It's kind of a mess. And I like this little cartoon saying that, yeah, it's hard to grasp what really people mean by causality often. It's not working. Oh. This one?
Yes.
Okay, it's working. So yeah, the question I try to answer is causality useful, in particular for decision making? And I argue that there are many approaches that try to use causality for statistical learning. So it's basically just for curve fitting. I argue that it's pointless, that it makes no sense. But it's it makes a lot of sense for decision making. So first, I'll review a bit what is causality, and in particular, do calculus, the framework of Tudor. So in causality, something you want to do is measure causal effects, right? So what I mean by that, if you see someone out the window with an umbrella, you can infer that most likely it's raining. That's a very strong indicator that it's raining. And that's a good statistical model for rain. If I observe an umbrella, I will observe that it's also raining. What if now I want to act in the world and I want to make rain happen? If you go out in the street and open an umbrella, it won't happen. So what was a very good predictive signal for an event is not a good cause for that event. You cannot act on that to provoke the event. So what you want to measure is the effect of interventions. So if you have two variables, A and B, you want probability of B given do of A. If I act, if I change the value of this variable A, how will that affect the distribution of variable B? You want to measure a causal effect. So to measure a causal effect, you can either do interventions. You do act in the world, you go out in the street, open the umbrella, and you measure the outcome, and you will see that there is no effect, it doesn't change. Or you can also reason with observations. You can just observe a system, you observe the variables of the system. And if you also have the knowledge of the causal graph, you know that this variable can affect this one, but not the other way around, for example, then you can reason using this distribution by using do calculus. So do calculus is a tool to derive causal statements from observational statements. Here is an example. Say that you have a system with three variables, A, B, and C, and you ask the question, okay, what is the effect of A on B? And here are three causal graphs. We study the three scenarios. In the first one, do calculus tells you, yes, it's identifiable, and it's trivially identifiable. You just have to measure P of B given A. If you do that in this graph, that's like a dependency graph. A is a cause of B, and this is a statistical path. A is also a cause of C, which is a cause of B. So when you measure P of B given A, you will have information that will flow from A to B through this path, which is causal. A is a cause of B, the arrow is pointing in the right direction. And also there will be information flowing through this path, which is also causal. A causes B, causes C, causes B. So if you measure P of B given A, you're only taking into account causal statistical relationships. So that's exactly equal to the query that you want. You can just measure that. Second scenario, the graph is slightly different. A is a cause of C and B is also a cause of C. So in this case, if you measure P of B given A, something actually happens. This path here going through C is closed. Because in graphical models, when you have a V structure, two arrows pointing to each other, if you don't condition on variable C, this path is closed. There is no information flowing from A to B through variables. So the only thing you measure is this arrow here, which is the causal. It's in the right causal direction. So you can just measure P of B. Last example is a bit more tricky because here you will measure A to B, the direct arrow, but also A, C, B. And this path is not causal. See that one of the arrows is not going in the right direction. So if you measure P of B given A here, you won't measure a causal relationship. You have to correct it, you have to fix it. And do calculus tells you, so yes, you can still measure your causal relationship, and you have to apply this little formula, which is called deconfounding. So you have to condition on variable C and take the average effect when you condition on variable C. So I won't go into details, but do calculus gives you this nice formula to measure your causal relationship. So in a nutshell, do calculus is a tool to connect observational distributions and interventional distributions. So what it needs is the causal graph. You have to know the causal graph. And then you can just observe the system, how the measure the distributions, and you can apply some formulas to extract causal effects. So you need observations and the causal graph. Some interesting cases where you will see that the calculus is useful. The nemesis of causality is confounding variables, especially hidden confounding variables. Say that you have a system like this one. So you know there are three variables. So you are interested in measuring P of B given do of A. But you know also that there is a hidden confounder. Okay. And you cannot measure it. You can only measure A and B, but you cannot measure C. So in that case, you only have the observational distribution on A and B. And do calculus tells you, no, there is no way that you can fix this. There is no way that you can close this path. So there is no way that you can recover a causal relationship. And this was an argument by the tobacco industry in the 70s, I think. So suppose A is smoking, B is cancer. You suspect that smoking causes cancer, but maybe there is a hidden gene that some people have that makes them want to smoke, and at the same time it causes the cancer. So then it's not the fact that you smoke that causes cancer, it's because of your gene that makes you at the same time want to smoke and have the cancer. And you cannot deny this argument. It's like maybe it exists and kind of makes sense. So you cannot just dismiss the argument. You have no way to dismiss the argument with only those three variables. But you can come up with fancy things which people did, and this is quite interesting. If you assume that there is a middle variable here, D, which is not caused by the gene. So this would be the level of tar in your lungs. So you can defend the idea that tar is caused by smoking. There is tar in smoke. And that tar, when it's on your lungs, causes cancer. And no gene can make tar appear in your lungs out of nowhere. So you can add this additional variable, and you can agree on this causal graph. If you ask experts, they will say, yeah, this makes sense. If you have that, what you can do is you can actually measure the causal effect from A to D, because this part has a V structure, it's blocked. And then you can measure the causal effect of D to B, because you can condition on A and apply this correction formula. So you have the whole formula at the bottom here to measure the causal effect from A to B. You don't need to know about C, you just have to observe A, B, and D. And you can recover your causal effect, and you find that, yes, smoking causes cancer. So causality is a useful tool to reason about like what's the cause of something. Can you give credit to a variable for having a causal effect on another one? And it's quite a powerful tool. Okay, so if you have any question, you want me to clarify something, feel free to ask. Yes. That does that. Here, you want to measure P of B given A, this guy, so those will be two values. And it's telling you that you have to integrate over variable A again. So it's just you sum over different values of A, values A prime. You sum over all the values of A. This is when you want to measure the causal effect from D to B. You have to fix by closing this path, this non-causal path. Yeah, going D, A, C, B. And you can close this path by conditioning on A. And this is this little formula. So it's just saying here on the right, you don't care about the value of A, you sum over different values, A prime. And you can look at books on, this is called the front door adjustment criteria from Judapper. It's very popular, you can just check online. Okay, so what about decision making? How could that be useful for decision making? So what is decision making? To me, decision making is making an intervention in a causal system to maximize a desired outcome, right? When you have an energy distribution network and you formulate a MILP to maximize your profit or whatever, you have knowledge of the system. You specify the causal system, and you specify how, if you turn some engines on or off, how that will affect your energy output or whatever. So you have a physical system, you know it's causal, you specify it, and then you say, okay, if I change some engines on and off, I intervene on the system, how will that affect some outcome variable? So in mathematical optimization, you solve problems of this type. Whatever function, constraint, unconstrained, you want to minimize something. F, this function would be the system specifications. They are given by experts, usually. And X is your decision variable. And you want to see which decision, which action will maximize this function F. If you look at reinforcement learning, so the simple case of bandits, right? It's not sequential, it's just one decision. Then it has the same form, you maximize because you maximize rewards, but it's exactly the same thing. You have system specifications which are unknown. You have to learn from data. When you take an action, you have to learn how it affects the outcome. And instead of X, you would write that A for action. You will act and see how it affects the outcome. In more general reinforcement learning, it's a bit more complex to write, but the idea is the same, essentially. You want to find pi, which is not a single decision, but it's a decision rule, a policy. So it's a rule to make decisions. And you want to maximize, for example, the expected reward, expected cumulative reward. And to do that, you have to know P, the distributions of your system, the transition distribution. So it's just your system specifications and the policy that you take. If you have both the system specifications and the policy, you can evaluate that policy and measure the outcome if you want. So it's the same idea. You have system specifications, decision rule, and the system specifications are unknown. You want to learn that from data. So it's very related. So you have decision making where the system is known, given by an expert. When it's unknown, you have to learn from data, and it can be sequential or not sequential. So you can kind of interpret all of that in a causal framework. And in this talk, I will focus on how can you learn the causal system from the data. So I won't talk about how you solve this minimization problem. This is what you guys are interested in and doing, but I will talk about the different problem. What if you don't know the system, you have to learn it from data. How do you do that? And so I call that causal decision making, or in the paper we call that causal reinforcement learning. But to me, it's really the same idea. Okay, so now I give you a toy example to like illustrate all of that. So maybe this is the most interesting example in the talk. I call that the door problem. It's a very simple decision problem. So you have a door with a light on it, it can be red or green. And then you have two buttons, up and down. And depending on the light on the door, the buttons will behave differently. And so one of them will open the door, one of them will not. And you can observe people interacting with the door. Push the up button, it opens, or it doesn't open. Push down button, opens, it opens. You're sitting on a chair and you're observing those people. Only problem is you're colorblind. You cannot see the color. You know there is something here, but you cannot see if it's red or green.
But the people opening the door, they know.
But sorry, if it
The people opening the door,
they might
interacting with the door, they know.
might know. They might know. I'm not sure. But yeah, the idea is that they know. And you ask the question, what is my optimal action? So, I tell you that the system is just very simple. If it's red, you have to push the up button. If it's green, you have to push the down button. Let's assume this system. So if you can see the color, the optimal action is obvious. If you don't see it, you're colorblind. There is still an optimal action. Imagine that most of the time the light is red. And what you want to do is you always push the up button. It's most likely to open the door. You like to learn this optimal action. So we have a causal graph with three variables. The state of the system would be the color. The action would be which button you press, and it might depend on the color. So people might decide to push a button given the color. And then the reward is, does the door open, yes or no? And it depends on the state of the system and the action. That's a very simple causal graph. What I want is this. I want the action which maximizes the probability of the rewards, given that I do this action. So this is my decision problem. And I don't observe S, I just press a button and I see if the door open or not. And what I can collect is observational data. So I can just sit in my chair and look at people interacting with the door. And that's very cheap. I just sit, I do nothing. I can look at many people interacting with the door, don't have to do anything. Or I can intervene on the system. I can get up from my chair, go press the button, see what happens. And you can assume that this is more expensive. I have to get up and so on. So I can collect both observational data and interventional data.
So,
yeah.
So, because now here you're pointing out something that I wanted to ask before in relation to the third blue system, which is so of course, I mean, you have this data and somehow I see you're thinking also about waste on the arrows, right? On the links from
yeah. I mean, there is no, by weight, you might mean the statistical strengths.
Yes, for example.
Yeah, yeah.
So, because that is also related. So, do you know if this entails some kind of hierarchical structure? For example, going back to the example of the smoking type, the farther you are.
Not necessarily, but usually the farther you are, the more noisy the relationship gets. But that's not really related to this, I would say. But yeah, there is a strength. It might be that there is no relationship at all. If people press buttons randomly, then the actions don't depend on the state. It might be, you don't know. It's just the causal system looks like that. Some of the arrows might have zero weight, no relationship. But you know that the system is like that. It cannot be in any other way. The arrows cannot flip.
Yes.
It's impossible. Like, you know, by design, the system is like that. And that's important. So you have knowledge of this causal graph. Okay, so you can see immediately that what I talked about, hidden confounder, you have it. There is a confounder between A and R, and you don't observe it because you're colorblind. So there will be issues. So let's look at that with numbers. So say that the state is, so I write 0 and 1 instead of green and red, but it doesn't change anything. Most of the time, the system is in state 1. Okay, 60% of the time, 40% of the time, state 1. And the transition model is, I have to do the action, which is the same as the state. So state 1, I have to press action 1 to open the door. State 0, I should do action 0. And say that the agents, the people interacting with the door, they behave like that. State 0, most of the time they press button 0, but sometimes they don't. And state 1, most of the time they press button 1, but sometimes they don't. Okay? Just they decide to do like that. Let's assume they do behave like that. If you just look at what people are doing, you measure this observational distribution, you will see that action 0 has a success rate of 80%. Action 1 has a success rate of 77%. So if you don't take into account confounding or whatever, you just use that to make your decision. You say, action 0 seems more successful, so I'll always press button 0. But this is not the optimal policy. If you do that, you will end up opening the door 40% of the time. But the optimal policy is to always press 1. And then you open the door 60% of the time. And this is exactly because when you measure this is not a causal relationship. It's an observed relationship. And if you make decisions based on this distribution, you will be biased. You will not make optimal decisions. This on the right is if you do imitation learning, say that from those numbers, you see that people press 0 30% of the time and 1 70% of the time. So say you just imitate, you do the same. And again, you're not optimal. You would end up opening the door 54% of the time, but this is not optimal. So if you do imitation learning or if you do decision making, which is not causal, you will end up taking non-optimal decisions. And do calculus tells you that actually. Do calculus tells you, in this case, there is a hidden confounder. The causal relationship is not identifiable. You cannot use observational data because it's biased. So you have to get up from your chair and you have to interact with the door. And if you do that, you will measure exactly this distribution, the causal one. And you will see that action 0 has a success rate of 40% and action 1, 60%. So you will infer rightly that the optimal action is always press 1. So we need the causal distribution. And do calculus does just that. It tells you here, from observational data, you cannot recover the causal relationship. You need interventional data. But it's a bit unsatisfying because I told you observational data is very cheap. This one is expensive. So could you maybe combine them?
And the question is also how many times do you have to press the button?
Exactly. So it's like a machine learning problem. The more data you have, the more reliable this guy is. So you would like to interact infinitely many times. But then the question is sample efficiency. Like at which point can you stop and you're confident enough that you're good? So that's exactly the question that we try to answer. You can do only interventions and say that after 100 interventions, you're good. Could you, by using observational data, could you do less interventions? Could you be more sample efficient? And that's the question that we try to answer. So to illustrate, so this was a toy example, but there is actually there are actually many applications, real world application where it makes sense. So the question is, when is offline data in reinforcement learning, when is it confounded? And it might happen in some situations. Think about self-driving cars. You collect data from human people driving a car. They have a wide field of vision. They can turn their head, see everything. They can hear stuff. They have a lot of senses. You would like to learn how to drive a car with just a tiny camera in front of the car. So you have a restricted field of vision. Then there is the data you observe. The agent takes actions based on hidden information. Say that there is a pedestrian on the side of the road. The human driver sees it, presses the brake pedal, the car stops, and the pedestrian crosses in front of the car. What the learning agent will see is There is no one. The field is restricted. The pedal is pressed, someone appears in front of the car. So it might learn the causal relationship. Okay, whenever I press brake pedal, someone appears in front of the car. So if I don't want anyone in front of the car, I should never press the brake pedal. So it's kind of an extreme case, but you see the issue here. So if you learn a causal model from data collected from human people, where you believe there is confounding, you should be cautious. In medicine, also, dynamic treatment regimes is a scenario where a patient comes in, you give them a treatment. So, for example, for long-term disease like cancer, a few months later, they come back, their symptoms change, you change the treatment, and so on. So you take sequential decisions. And say that you collect medical records from people, and you want to learn a causal model. Like you want to learn which medicine should I give to people given their medical history. The problem is there is a lot of information that is lost in the patient-doctor interactions. The doctor will touch the patient physically, will see stuff, and they will not write everything on the medical record. So you will be missing information on what the doctor actually used to make its decisions. And it can lead to poor causal judgments, like if you see someone taking vitamin D, like an old person taking vitamin D, you can see, this person is very likely to get osteoporosis. And that's a good observational statement. Because the doctor knows this person is at risk of osteoporosis, so the doctor decided to give them vitamin D, because vitamin D actually lowers the chances that you get osteoporosis. But if you just look at observational data, I see someone taking vitamin D, I can infer, no, they have higher chances of getting osteoporosis. So again, confounding in medical data is happens probably a lot. Last word on Atari video games. So if you do reinforcement learning, like people like to do in machine learning with video games, human players, they have the screen. That's the only information they have. And the learning agent that you train, they also have the screen, the pixels. They have the exact same information. So there is no confounding. If you collect data from human players playing Atari video games, there is no confounding. You don't have to worry about it. So sometimes just by thinking about the system, you can decide if you take the chance or not of ignoring confounding. And yeah, the point is, at least in those two cases, offline data is cheap. You can collect data from human drivers, from doctors, but online data is expensive. It's hard to get your agent drive a car and hit a building or whatever. It's just too expensive. Yes?
What if in the Atari it was more like a POMDP? Would it be confounded?
No, so the same holds with POMDP. Yeah, you can show that.
About observability.
No, it's more about like, do the learning agent and the agent that you observe, do they have the same information?
I see.
Yeah. And yeah, the question I asked is, can offline data be useful? So do calculus that you know, you have to ignore it, but do you just have to dump it away? Because you can have billions of data from self-driving cars, from human drivers. So do you just have to throw it away, or can you use it more? So you have to move beyond do calculus to use this kind of data. And so that's what we did in this paper that you can find on arXiv. We call it causal reinforcement learning. So what we do is basically, so I go very quickly on that. We take both data from the observational regime and the interventional regime, and we label this data with an additional indicator variable. 0, it comes from the observational regime, where there might be an arrow here. 1, it comes from the interventional regime, where I know that there is no arrow here. And you can mix this data together to learn a latent variable model. So this guy here. So this is how you fit this model. So you fit a latent variable model with those 3 variables, R, A, I. And you have this additional constraint. It's called contextual conditional independence. When I is 1, there is no relationship between Z and A. So the strength of this arrow would be 0. Like when I is 1, there can be no dependence between A and Z and A. So it becomes a really standard latent variable model. So you fit it like that. This is the constraint that you add to the model, but it's very easy to add this constraint, and then you can learn it with any latent variable learning algorithm, EM. It's just a very standard model to learn. And if you do that, you feed this latent variable model, you will find a compatible confounder. You will not recover the true confounder, but you will find a compatible one. And if then you apply the deconfounding formula to get back the causal model, this guy will be stronger due to the observational data. And you can show it. So yeah, there are a few variants that we'll compare. Basically, in the data, I told you that you mix the observational data, you just add a label 0, and you mix also interventional data with a label 1. So you can mix all of the data, learn your model. You can only use interventional data if you want and learn your model. This would be no ops. Augmented is when you mix it with the method I described. And you can also do a naive approach, say that you ignore confounding and you use the observational data as if it was not confounded. And that's the naive method. So we'll compare those three methods. You can show that theoretically, if you have infinite observational data, the augmented method has bounds. You can derive bounds on the augmented method. It is bounded between two values, which depend only on the observational distributions. So using the observational distributions bounds your model. Because your model is bounded, it's more restrictive, and it will be more data efficient. That's the argument for why this works. In POMDPs, which are more complex, it's sequential, you can do exactly the same. Everything I told about, you can do for POMDPs. And we did some experiments with POMDPs. That's a grid walk problem where you are here, you want to go here. And the learning agent doesn't have the full information. It has you can see the state of the game only once every 5 frames, something like that. But the expert sees the full state of the game. So there is hidden information, there is content. And if you compare when you learn with the augmented methods, you converge faster to the true causal model. Naive method also converges faster than not using any observation. And this is what you get if you don't use any observation, if you only rely on interventions, you converge slower. And in terms of rewards, the augmented method is the most data efficient. It starts getting a reward earlier on, and then it gets better rewards. And you can see that in runs, if you do runs of the agent that you get, if you don't use observational data, so this is at when you collected 128 samples. If you don't use observational data, at this point you don't even learn to cross the wall. With the naive method, so you use the observational data, but it's confounded. You also don't learn how to cross the wall. And you see that with our method, it efficiently uses the data and it starts learning something interesting at 128 samples. So it's like 2 orders of magnitude before the method that's not using observational data. So it's actually working. Some final words. Yeah, so this work that I described, we only tried it on toy problems. We would like to expand that to more challenging problems using maybe real data in the medical domain or in robotics, maybe. We like to try other training algorithms. And there is a paper that is very related, in which they don't take causality into account. And we would like to add causality to this paper, see what happens. There are some extensions that we consider, like you can consider what happens if the confounding variable is hidden only on the observational regime. So there are many variants that you can consider because the setting I described is not universal. The paper is online if you want to check it. And the take-home message for this, for this community, I would say, is pay attention to confounding in your data. It's very tempting to try to learn a causal system, to learn the system specifications from data. It's what many people are going towards. But then you face the danger of confounding. So you have to make sure that you have strong arguments to say that no, there is no confounding. Or if you believe there is confounding, then you have to take it into account. You have to think about it. So it's good to be aware of that issue. That's it. Thank you.
Thanks.
Maxime.
Any questions?
Okay, maybe I can pick up. So if I understand it, the main point is confounding, and what you do is you intervene, and by doing this, you bypass the confounding factor.
Yes.
Which means you need to know the graph to know that when you intervene on this point, you will bypass the confounding factor.
No.
Not another.
So if you do interventions, you don't need to know anything about the system. You have to make sure that, so in medicine, you do a double-blind random trial. You take two populations, you give them a pill, you just change the compounds inside the pill. So the only thing that you change is the chemical inside the pill. You make sure that everybody is blind, the doctor is blind, the patients are blind. And whatever you measure after that will be a causal relationship. So if you do randomized trials, you actually measure causal relationships. And that's a requirement to measure like how effective is a drug and stuff like that.
Yeah, I was thinking more of the door example.
So if you press the button and you notice that when you press button A, it opens the door 60%, and when you press button B, it opens 40%. You know it's a causal relationship because nothing else can change if the door opens yes or no.
Oh, that's your assumption, isn't it?
No, I mean,
if you have a more complex problem, maybe you intervene on some part of the environment.
Yeah.
And this gets processed.
Yeah.
Or you have other nodes, and in those nodes you have confounders.
Yeah.
So can you intervene in any parts of the system, or do you have to intervene at a specific part of the system that you know that you will bypass, or I don't know?
No, you don't have to know it will bypass. So when you intervene on a system, say like this one. So this is your system. Yeah. If I intervene on variable A, this arrow disappears because I force the value of this variable. I know that nothing else says how A changes. So this arrow disappears and the confounding disappears. If there is any confounding, it disappears. And this is proven.
Yeah, but this is because you know that you have these three nodes and how they are linked.
There can be more. The path can be very long with other variables and other stuff. They can actually. No, it's
and
always.
You have B on the right and B also impacts on R. And then.
Yeah, and then you measure a causal effect. Yeah.
Okay.
I mean, it can get more complex. You can do contextual causal effects. What if I know the value of variable whatever X here, and I intervene on A, and you write that as it would be, for example, P of R given do of A, I act on A, comma X. Given that I observe that and I do that, what is the causal effect? And it's still valid. You can still reason about that.
Okay.
Yeah.
That's it. So I don't have, it's not very clear in my mind, but this isn't in a sort of sense a preliminary step to do game theory. So in game theory, the point, for example, think about the bi-level programming problem,
yeah.
right? I mean, there is some upper level decision maker, and then some lower level decision maker. The reason why this has been designed in the 70s, I think, or even earlier, this was because you wanted to, in a certain sense, I mean, the upper level, so the lead, leader was actually imposing some decisions, and the follower optimizing their own objective function were actually obtaining results that were not really related to, or at least not the one that the leader was actually thinking of, right? I mean, there was a confounder in between, which was the fact that the follower were having their own objective function to optimize. So it seems to me that in this analysis, I mean, there's something similar in a certain sense. I'm not, I don't know, it's not clear in my mind. But what is missing is that the objective function. So the door doesn't have an objective function. It acts essentially as is. Instead, when there are players, essentially they have objective functions, and so maybe this framework can be used for somehow. I mean, somehow I don't know, learning the objective function of the sector of the follower or something like this. But to me, it seems to be there is some connection into that. I don't know. I'm just tell you to think about it. But I'm sure that you can talk to a lot of people. But it seems to me that there is some relationship on this, because the compounder is the fact in game theory, at least in mathematical, in bi-level games or multi-level optimization, is the fact that, I mean, you do some action and you impose some taxes, for example, or actually originally it was imposing some policies on I think like World Food Organization, right? I mean, policy putting like some incentives to farmers, and the farmers were actually taking the incentive and doing something else, right? I mean, and so the compounder was the fact that there was an objective function sometimes over the player that was actually changing the effect of something that you had in mind. So now, in your context, the door doesn't have an objective function. It acts precisely like you tell according to this distribution. But maybe there is something to be looked at in this direction.
Yeah, I think you can formulate like bi-level optimization as causal graph. And then you can reason about causal effects and causality. And I think confounding does not necessarily come if you have different objective functions. But it comes if the second player, they use information to make their decisions that you don't have. If they use additional information that you don't have, so you assume that they will take the optimal decision given that they know, I don't know, the superficie of their land and whatever. But if you miss that they take their decisions given other information, they have access to more information than you thought, then there will be a confounding effect.
Yes, but the point is that the objective function of the farmer in this context could be seen as an additional information that you don't have as a leader, right? I put something, and then the objective function of the farmer is because he knows that, I mean, it may change because you say it doesn't have information, because he or she wants to actually use the land differently from, and then it can be translated into an objective function. That's the point, probably. But it's a matter of, I mean, formalizing this and probably like, I mean, mapping it into your formalism grammar. I think it's actually for that.
There are many things that you can re-express as causal graphs, but that people knew for decades and they know how to fix it. Just do calculus is kind of an elegant way of formulating things, and it's kind of a universal language to talk about causality. So it's a good tool to know.
Master.
To master.
Probably a stupid question, but can all the confounding be modeled by a single variable?
Yes.
Always?
Yes. That's a good question, and that's what we assume in the paper. So all the confounding variables, you can assume is just one big multivariate variable, and then you're fine. So the compatible confounding variable that we learn here, that we learn a single confounding variable, but we make it large enough. It can have, I don't know, 200 modalities, so that it can model.
Makes the entire process a lot more simpler, right?
Yes. So the modeling process can be simple. You can just use one confounding variable, but if the actual system has more, it's fine. You can fit all of that in one confounding variable.
Okay, maybe we'll take the other questions offline because we're a bit out of the.
Maxime.
Thanks, Maxime, for the talk, and thanks also to the event.